Have you ever wondered why time seems to run differently for astronauts in space? Or why GPS systems need to account for Einstein's theories? The answer lies in relativity, one of the most profound concepts in physics, strangely when you're moving fast or near a massive object. Or why the laws of physics seem different in different places. These puzzling questions are answered by the theory of relativity, proposed by Albert Einstein over a century ago. This groundbreaking theory reshaped our understanding of space, time, and gravity. What is relativity? Relativity is a branch of physics that explains how measurements of space and time change depending on the speed and position of the observer. Before Einstein, people believed space and time were constant and absolute, the same for everyone, everywhere. But Einstein showed that space and time are flexible and intertwined, forming what's called space-time. In 1905, Einstein introduced special relativity, which applies when objects move at constant speeds, especially speeds close to the speed of light. One key idea is that nothing can travel faster than light in a vacuum, about 300,000 kilometers per second. Special relativity says two important things. 1. Time dilation. Time itself can slow down for objects moving near the speed of light compared to a stationary observer. So, a fast-moving astronaut's clock would tick slower than one on Earth. 2. Length contraction. Objects moving near light speed appear shorter in the direction of motion to an outside observer. These effects only become noticeable at incredibly high speeds, but they prove that time and space are not rigid and absolute. The famous equation E = mc2 comes from this theory, revealing that energy and mass are interchangeable. This relationship is fundamental to nuclear energy and particle physics. 10 years later, in 1915, Einstein extended his ideas to include acceleration and gravity through general relativity. Instead of seeing gravity as just a force pulling objects together, Einstein described it as a bending or warping of space-time caused by massive objects like planets, stars, or black holes. Imagine a stretched rubber sheet. If you place a heavy ball on it, the sheet bends and smaller balls nearby roll toward it. This is similar to how space-time curves, guiding objects along curved paths, what we experience as gravity. General relativity predicts phenomena such as gravitational waves, ripples in space-time caused by massive cosmic events, which were directly observed for the first time in 2015. Relativity isn't just abstract theory. It directly affects our technology and everyday life. GPS satellites. Because they orbit high above Earth and move quickly, their clocks tick differently due to both special and general relativity. GPS systems adjust for these changes to provide accurate positioning worldwide. Astrophysics. Predictions about black holes, the expansion of the universe, and cosmology all rely heavily on general relativity. Particle accelerators. Understanding how particles gain energy and mass relies on relativistic physics. Einstein's theory of relativity fundamentally changed how we see the universe. Time, space, and gravity are interconnected and flexible, far from the absolute concepts once believed. This shift opened new doors in physics, enabling technologies like GPS and deepening our understanding of the cosmos. Relativity teaches us that the universe is far more dynamic and mysterious than we imagined, and there's still so much to explore.